Good evening, ladies and gentlemen. Welcome to the international webinar on Smart Material Temperature-induced Safe Memory Allows, organized by IRAJ Webinars in association with ITR Group. On behalf of entire organizing committee, I'm Isaac Behera. Organizing secretary would like to welcome you all for this webinar. Ladies and gentlemen, let me introduce our organization. The motto behind this non-profit association is to bridge the gap between students, professors, academics, and industrialists from multidiscipline. Apart from organizing various seminars, expert talks, and conferences, we have various highly rated multidisciplinary journals in the field of science, engineering, and technology, and management. Since our inception, we have been arranged various international conferences at various parts of the world, like New York, London, Australia, Hong Kong, Dubai, Bangkok, Kuala Lumpur, India, etc. More than 1 lakh people across the globe are associates with us, and more than 5 lakh research papers have been published during our journey. Today, I'm glad to welcome you all as a member of this fastest growing network for the advancement of science and technology in terms of research and innovation. Today, we were very much fortunate to have an eminent professor and expert who is joining this webinar as an expert speaker and guest. His name is Professor Ajit Behera. Presently, he is working as a professor in Department of Metallurgical and Materials Engineering at National Institute of Technology, Rourkela, India. Now, I'd like to welcome our Professor Ajit Behera to deliver the webinar.
Hello, is it audible?
Yes, sir.
Okay. Now I'm going to share my screen. Okay, is it visible clearly?
Yes, sir.
Okay. Good afternoon, all of you. First of all, I will thank IRAJ team and coordinator to invite me in this platform. Okay, today my topic of presentation is smart material, that is temperature-induced safe memorial. Right. In this presentation, I will discuss on what is smart material, what is safe memory alive, which is comes under this smart material classified material, and then fundamental principle for type of fundamental things are present in with respect to different type of applications and various emerging applications we will discuss here. Okay. So what is smart material? As for definition, just before definition, I will show you a video clip here. You observe there how nature will give a indication how to realize what is smartness of different type of material. First, I will show you a video. So in this video, you observe that when there is a force or stress that is experienced by the surface of that plant, then according to that stress or pressure on the surface, it will close. Okay, that is called smartness. Okay, according to the force, it will close its petal or different type of things. Okay, same thing will observe in case of material, right? Same thing, it will happen in case of material. So as per definition, smart material design can be significantly changed in a controlled fashion by an external stimuli, right? So here in this video, you observe that the stress is a external stimuli. According to that, it will actuate, right? So in case of material, different type of stimuli are there, that is stress, moisture, electric field, intensity of light, temperature, pH change, and chemical compound. These are the stimuli. Okay, by this stimuli, the material will experience and actuate accordingly. Right. This smart material is also known as intelligent material or responsive material. Right. So different type of smart material are piezoelectric material. These are the material which can produce electricity when it will experience the stress. Right. Second one is safe memory alloy or safe memory material. This is a type of material which can actuate or which can change its dimension according to the stimuli, that is electric field, magnetic field, or stress. Right. Another one is electrostrictive material. It produces electricity when we will give pressure as the stimuli here. And then magnetostrictive material, here the external stimuli is magnetic field, and reverse also stress. Right. And self-healing material, it is also the stimuli is temperature, field. And in case of pH responsive or sensitive polymer, here the stimuli is pH change. And in chromogenic system, it is a smart material which can change its different parameter according to the intensity of light or thermal. Okay. Main thing is that chromogenic system, it will change its color. Okay. It will color by the help of different external stimuli. Then smart fluid, it is a rheological fluid, and it can change its viscosity and physical property according to the stimuli, that is electric field and magnetic field, right? So all this just you overall you have known, that is smart material. But today presentation we will discuss about safe memory material. Okay. So what is safe memory alloy? So as its name, it is memorized shape, right? So alloy, these are the alloy that remember its that shape after being deformed, okay, by the application of external stimuli to the alloy. So this type of alloy is also called as memory metal, muscle wire, smart alloy also. Okay. So before going to the definition of this safe memory alloy, I will show a video clip here. What is the difference between the conventional alloy and safe memory alloy? Right. Suppose we are taking here a brass, and if you will give force or we will deform it, then what happens? Then it will be uh, like that. But in case of safe memory alloy, if we will deform the material, then it will come back to its original shape. This is a type of pseudoelasticity nature of safe memory alloy. Okay, you here in this video, you saw that when you will give some amount of pressure here, or we want to deform it, then it will come back to its original shape. Okay. This is the beauty of this type of safe memory alloy. So as for definition, safe memory are the alloy, if we will give some amount of deformation, then to that deformed dimension, if we will give some external stimuli, that is thermal energy or magnetic energy or electric energy or sometimes stress, by the help of this external stimuli, we can recover its original shape. Right. This is called as safe memory alloy. So, what is the potential property or function of safe memory alloy? Why we are not going to different type of smart material use? Because so many type of smart material are there, because uh, in current edge, all the type of smart material that are used in sensor and actuator applications, right? But why we will choose safe memory alloy? rather than other type of material, because due to this advantageous property, that is first one is biocompatibility. Okay, SEP memory alloy, that is first one is biocompatibility. So most of the alloy is biocompatible in nature, because it can be it will not produce any type of toxicity, or if you will implant it in different type of biomedical applications, right? And another one is corrosion proof. Most of the SEP memory alloy, that composition is such way that it can give better corrosion resistance property, right? It have better sensing power, and accordingly it will give or it will have energy absorption capacity. Accordingly, it will actuate. Okay, um, then it have a high impact resistance, good damping property, right? And with respect to this property, uh, in addition to that, we can get two type of peculiar properties, that is self memory effect property and pseudoelasticity property or super elasticity property. By these two property, it is the main property of self memory alloy. By this two property, we can apply in different type of application. We will discuss in this presentation. So as comparison to other smart material, when you will compare actuation stress with respect to actuation strain, then you can get safe memory alloy here, right? So think about that. Why you will not go for safe memory alloy when the conventional smart material are used? Suppose I will give you an example, that is in actuator application to produce some sound in sonar transducer. So there we can use piezoelectric ceramic type of material. But in that actuation case, if we operate by temperature induced or magnetic induced self-memory alloy, and we will actuate in such way that we will actuate the dimension in such way that it can produce that desired frequency of wave. So we can use it. Uh, Definitely will get a better that result, right? So what is the main thing? What is the main principle behind the set memory alloy? Okay, so that we can use this type of alloy in different application. So here I will give I will show you one application for set memory alloy. Then according to this application, I will discuss about the fundamental thing behind it. Right. You just observe here. There is two wheel, and this two wheel is connected with a set memory alloy wire. Right. Set memory alloy wire, and no other additional source is attached with it. There is a supporting element and two wheel and connected by a set memory wire. And just below it, you can see this is a bowel that is contain water that is heated by sunlight. Okay, just 2-3 degree above than that of normal temperature. Right. So this setup, when we will lower the bottom wheel, and when it will touch to this liquid, water liquid, then it will start rotate. Okay, just see this video. So what happened with this type of material? Right, no other external source is there to rotate this wheel. Even it will rotate by the when it will touch with that of water liquid. What is the fundamental thing behind it? Right. So we'll go to the macroscopic and microscopic view of that string, that wire, which is connected with this two wheel. Okay, what happened inside that material, so that without any source we can rotate a system. So to understand that one, I will tell from origin. Suppose there is a straight dimensional bar is there, shape memory alloy bar. Suppose you can consider it is a original shape, right? And here you are deforming the material. Suppose in second step you are deforming the material. This is the deformed shape, right? Consider this is a deformed shape. So here you want to about the original shape. Okay, you want to come back to its original shape. So how we will how we will recover this shape? Then if it is a temperature induced shape memory alloy, then you have to give heat as an external stimuli, right? So at a higher temperature, the structure you will get, okay, or you will recover the structure, which is looks like same as that of original, but microscopically, when you will observe, it is not equivalent to that of original shape, right? Remember. So this hotter shape, in this step, you have to cool it. By cooling, you will get same shape, but microscopically, it will arrange same as that of original shape. Now you can tell it is the cooling shape is equivalent to original shape. Okay. So what is the difference between this hotter shape and the cooler shape? Here we'll go to the atomic arrangement in between this material, right? Suppose this one is a low temperature shape, undeformed shape. Suppose you can consider it is a atomic arrangement in original or initial shape, right? And undeformed shape, in case of shape memory alloy, it is always martensitic structure, okay, low temperature shape, martensitic structure. And this martensitic phase, the atomic arrangement is just like twin. You know, twin is a it is a surface defect for conventional material. But here, in case of shape memory alloy, you can consider this is a atomic arrangement, just like a twin-like arrangement, right? And this low temperature martensite undeformed phase, when we will apply stress to deform it, then what happen? The atomic arrangement, again it will form twin, because original or initial shape is twin-like arrangement. Again we will give deformation, again it will form the twin. Okay, so it will form a this type of shape, just a rhombus type of shape. That is called detwinning, detwin martensite. Okay, because all the deformation we are doing in that without temperature, or here we are not um, this time, this day up to this step, we are not giving any type of stimuli. So at that low temperature, this is also martensite. So after deformation, the structure will be like rhombus, right? And again, here you want to recover the original shape, right? So here you will give external stimuli heat. So by giving heat at a particular temperature, the atomic arrangement will be like this cubic type of atomic arrangement. And at a high temperature, this cubic shape, that the phase is called austenitic phase. So initially it is a martensite phase, low temperature phase, and by giving external stimuli, you will get austenitic phase. Okay, in austenitic phase, it will relieve most of the internal stress, and by cooling to this high temperature shape, again by atomic stabilization, it will form the twin-like arrangement again. Right. So all this transformation will happen in that type of material, that is shape memory alloy material, and all these transformation are called solid state phase transformation. Okay, although phase transformation will occur in solid state only. And all the transformation will happen in a coordinately manner, so that it is called military transformation. You know about civilian transformation and military transformation. Generally, civilian transformation will occur in case of conventional material or traditional material. Suppose in case of steel, iron carbon system, if you will give some amount of heat, then you can get a carbon atom that is from one interstitial site to another interstitial site. So it is a very random manner, so that it is called civilian transformation. Why it is called civilian transformation? Because suppose one man is going to buy some vegetable to market, it is not possible to go coordinately manner and very periodic manner to buy the vegetables. So you have to go very randomly here, there, and to buy the vegetable. So when you compare a large number of people in a market, they will randomly go here, there to collect the vegetable. Same thing occur in case of conventional material. When you will give some amount of energy to it, then atomic jumping will be there. So that is called civilian transformation. But in case of safe memory alloy, it is a particular transformation that is called military transformation. You can observe in military marching, right? And in marching, the hand and leg, they are moving in a coordinately manner, right? The one person movement is equivalent to that of surrounding person movement. So same thing happen in case of safe memory alloy, very coordinately movement. That's why it is called military transformation, right? Whatever I am showing here, in case of safe memory alloy, the atomic arrangement and atomic movement or displacement, everything will be by a coordinately manner. So that here all the thing will describe or will explain. That is military. And here there is no diffusion will occur. So that fixed diffusion law will not work here. And in this mechanism, this low temperature martensite to high temperature austenite, conversion in between that, the twinning, detwinning mechanism will be also play a big role. Right. So come back to that application. I have shown you that without any external source, by the help of hot or liquid, how we will rotate a wheel. Right. So just compare. Suppose the shape memory alloy where initial shape is straight. Okay, initial shape is straight, and this initial shape, you know, it is a martensitic phase. Okay, twin-like structure. And now you have to wind this wire with this wheel. So you have to deform it, okay, by applying load, or you have to deform it and you will fix in between this two wheel. Once you are deforming this side, suppose these are straight and straight, but here and here it is deformed condition. So it is a shear-like shear dominant transformation here. And here, when it will touch with the external stimuli, that is temperature, in the form of water liquid, then what happen at higher temperature? This shape, it will transfer to the cubic shape. Okay, so once it will form the cubic shape, then it will try to attain the microscopical dimension that is same as that of original shape. So it want to tend to become a straight, right? So this line, when it will expose to hotter stimuli, then it want to straighten it. So it will pull and it will come to this side. Once it will come to this side, sequence wise, whatever the portion it will come in contact with liquid hotter medium, then it will go in that direction to become a straight line. Straight. So in this way, we can rotate the wheel. This is the mechanism of shape memory alloy. So whatever the deformation you will give by different application, whether it will rotate towards left side or right side according to the different deformation or uh, structural arrangement of that system. So whatever you will give the external stimuli, the temperature as a temperature, then it will form this cubic step. Okay, it is a final. After that, it will straighten. So here it is a high temperature phase, that is austenite, and this is the low temperature phase martensite. You know the shape change and this actuation mechanism or straighten mechanism or come back to its original shape. All the thing it will happen in between this high temperature and low temperature shape, austenite to martensite or martensite to austenite. Right. When you will observe in a scanning electron microscope, what happen inside the material or microstructure. In microstructure, you can get for austenitic phase, it is just a smooth type of surface. But when it will come back to its different phase, that in martensite, you can get feather-like type of structure. Right. So here I will show you a video clip that is in situ video that is camera arranged with the scanning electron microscope. What happened for a shape memory alloy in case of pseudoelasticity or superelasticity behavior? When suppose it's initial shape is one phase, and by giving stress, it will come back to its another shape. Again, it will converted to as usual shape. Okay, just I will show you a video here. This is pseudoelasticity nature. This is smooth, that is a austenitic phase. Then when you will give pressure, then it will form the martensite type, martensite phase. Again, by relieving stress, it will again smooth type of surface you will get. Okay. So to another peculiar property of shape memory alloy, that is we'll discuss here, that is shape memory effect and pseudoelasticity. Pseudoelasticity also called as superelasticity. Okay, these two type of property you can observe in different type of application for in case of shape memory alloy. Okay, what is shape memory effect? So in previous slide, whatever we will discuss, that is shape memory effect. After deformation, when you will give some external stimuli, it will come back to its original shape. That is called as shape memory effect. What is superelasticity? Another behavior. So this is the type of application we have to train the material in such a way that the martensitic to austenitic transformation, and we have to maintain the working temperature is just above austenitic finish temperature. Okay, at that temperature, whatever you will give some any type of stress, then it will change from austenite to martensite. Then it will come back to martensite to austenite. Okay. I will show you some video of this two property. Then again, I will discuss about this two behavior, how it will distinguish by stress and temperature diagram. Then it will be better to understand. For shape memory effect, suppose this is the he deformed the material, and externally he will give some heat to come to recover its original shape. This is called shape memory effect. But in case of pseudoelasticity, this is the shape. Whatever you will give stress or you will deform, there is no need of external temperature. Without external stimuli, it will come back to its original shape. This is called superelasticity or pseudoelasticity behavior. Right? Why it will happen? We will go to the stress strain temperature diagram. You can better understand here. Okay. So first one is we'll discuss about shape memory effect. Suppose this is the origin, and initially, it is shape memory alive, and original metallurgical phase is twin-like structure, right? Twin-like structure. So here we will give some amount of deformation. So by giving some amount of stress to deform it, it will follow this path. It will follow this path as like conventional material, right? And it will form a shear dominant transformation. Okay, that is D2 in martensite, which is in stress condition. And when you will relieve the stress, then it will come to this point, the D2 in martensite, which is on stress condition, right? On stressed condition. So here we have to think how to recover the material, because all the thing stress strain diagram we have given the stress, it will follow this path, and very small recovery are there after relieving the stress as like conventional material. And at this point we are thinking that how we will recover to this the initial set. Okay, so this is the main path where we have to give some external stimuli as heat. Right? Then it will follow this path. It will follow this path up to the temperature when we will give above than that of austenitic finish temperature. Right? Then at high temperature, that is austenitic finish temperature, it is a cubic like structure. Right? It is a cubic structure. And when pull it, think like microstructure like structure. Here we will get original shape. So this path is called as shape memory effect. Shape memory. Again, what about super elasticity, right? Super elasticity. Super elasticity, I already that we have material which is above than austenitic finish temperature. Operating temperature is austenitic finish temperature. So here it is completely different from that ceremony because the initial, the original or phase, austenitic phase, and give amount of stress, and it will form martensite, D2 martensite, right? And when you will leave the stress, it will suddenly come back to its austenitic state. Okay, this is induced phase transformation. Remember, this super elasticity behavior is used. There is an example I will show you. There is a spectacle frame that is made up of set memory alloy. When he will deform the material at that room, that material is working temperature is above austenitic finish temperature. Whatever he will give force or deform the material, it will come back to it also. Right. This is the property of pseudoelasticity. So how memory effect, and another side is pseudoelasticity. Uh, just like material particular manner. It implies that material to in a certain way, and that material uh, Is it audible?
Yes, sir.
Okay. Actually, there is an internet interruption. Okay, we'll continue. So we are at training procedure because in case of set memory alive, whether we'll go for set memory effect or pseudoelasticity behavior, we have to go for a training procedure to train the material. So how we'll train the material? Just observe this video. Suppose this is a straight set memory alive. We want to train the material in this set. Okay, in this set. It is a simple example. So in this set, we have to heat at a constant temperature, at a higher temperature. Then we'll cool it, and this procedure again and again we have to do. Okay.
Sir, sorry to interrupt in between. Can you please share your PPT?
Okay. Is it visible?
Yes, sir.
Okay. So in training procedure, we have to train the material in a particular way, right? So I will show you a little one example, very simple example, how we will train the material after fabrication. Suppose there is a straight bar, and we will make a shape, just a simple shape, and to keep that shape as a original dimension or original shape, we have to heat it at a high temperature. Then we will cool it, and again we have to do this procedure so that it will form the original shape. We make the original shape here, and after deformation by giving small amount of heat, it will regain its original shape. Okay, another example is here. Suppose from straight bar we have to keep this structure, the star-like structure, as original shape. So we'll put inside the furnace, and we'll increase the furnace temperature. Okay. Again, we'll put in a cold medium. Okay. And again and again, we have to do this procedure to measure this angle. Suppose this angle, whatever we'll fix in that board. Okay, this angle we have to maintain. Suppose we will keep in furnace, we will cool it again and again. We will do it by removing this shape. If it will maintain that angle only, then we'll tell that it is already trained. Otherwise, we have to follow this procedure, heating and at that heating and cooling, right, in that loading condition. So we have to train in this way. One thing is that many set memory alloy will cease to generate plastic strain. Okay, main aim is we have to cease the plastic strain after sufficient cycling, and it stabilizes the overall material response. Such repetition until stabilization is referred to training. Okay, remember, such repetition until stabilization is referred to training. What is the stabilization? We have to cease the plastic strength, right? So training is often performed by applying many stress cycles while maintaining a constant temperature. So according to this training procedure, we can categorize this set memory alloy into two types. One is one-way set memory alloy, and second one is two-way set memory alloy. In case of one-way set memory alloy, we will the material can remember only hitting shape. Okay, because this is the initial bar. We'll deform it. Then by giving temperature after cooling, we'll maintain the same shape. Okay. But in case of two-way shape memory alloy, severely we will deform. After that, it will remember a heated shape, then lower temperatures than that of previous one. It will also maintain another shape. So two type of shape it will maintain. Okay, at two different temperatures. So that it is called two-way shape memory alloy. Here, there is a training procedure how to make this one-way shape memory alloy and two-way shape memory alloy. I will show here. Suppose in lab scale, you can also train the material. You can take some plaster of Paris and this shape memory alloy spring. Suppose this is the where you have to make a structure, your predetermined structure. You will keep inside this plaster Paris. Then you will dry it. After drying, you will put inside the furnace. So after drying, he's removing the that is vulnerable material. Then keep them inside the furnace, right? So inside the furnace. So this procedure, heating and cooling at that particular shape will be repeated. I'm showing you. You can use it in your lab scale. That's so. At last, you will get a shape after removing from that solid material, that is trend shape memory alloy. You will break it, and we have got this shape. Okay. And after deformation, he stays to deform it. And by giving some external stimuli, it will come back to the original shape. Okay, this shape he tried to make here. And in case of two-way shape memory alloy, what happened? Suppose it is a cold medium and it is a hot medium. Suppose this spring, you can observe. So here spring, you can see the length of the spring. In hotter medium, it is squeezed, and cold medium, it is expanded. Okay, so two type of shape it can remember. So first thing we observe that after fabrication, shape memory alloy training is must to attain that shape memory effect and the pseudoelasticity behavior. Okay. Another thing is that material cadmium memory, memory, induced shape memory alloy you have to uh, make. Okay. But gold cadmium, whatever you will take the percentage, atomic percentage here, it will not give shape memory alloy property. There is a particular percentage you have to take, because in case of gold cadmium, you have to take 46.5 to 50 atomic percentage of cadmium with balanced amount of gold. With this composition, when you will fabricate and train the material, then you will get shape memory alloy property. If you will go beyond this limit, then you will never get shape memory alloy property. Okay, remember this one, because and another commercial based shape memory temperature induced shape memory alloy is nickel titanium. If you will take nickel 5% and titanium 95%, and you will tell that it is a nickel titanium alloy, and I know that nickel titanium, it will give just shape memory effect property, but it will not give memory effect property in this composition. So you have to take nickel titanium. Suppose nickel is 45 to 0.5 to 55% range. In between this range, you have to take nickel with balanced amount of titanium. So to go for set memory alloy fabrication and training procedure, you will keep focus on this composition also. Right? So these are the different example of set memory alloy. And now we will go for industrial application. Okay, how this principle and this training procedure, how we can use in different type of application. So here I will discuss only for emerging applications. First one is force actuation, which is used for rock hardness measurement in different planet, which is used in rover, right? And also rover wheel, solar panel opener, asteroid damper parts, satellite detachment, temperature control system, cryofit tube coupling, biomedical stand, dental wire, bone fixation, eyeglass frame, blood clot filters. So in this emerging field, we can use this shape memory alloy um, in comparison to other smart materials, right? So one by one, we will discuss here. Force actuation. Force actuation, it is a constant two type of that is unconstrained and constrained type of this force actuation mechanism for rock hardness measurement. So here for unconstrained, it is the initial shape, and we will stretch it and fix in a flexible line or wall. Then by hitting, it will come back to its original shape. Okay. It will only recover the shape without giving or without exerting any type of force here. But in constant type, what happen? We'll stress the material, we'll fix the in the fixed wall. Okay. And when we'll hit it, it tend to squeeze it to gain its original shape. So what happen? It will give some amount of stress here. Okay, and that stress is used in different purpose. Here I'm showing the stretch tension type of force here, but sometime in compressive type force will stress will give here, and by fixing two side, and if it will not able to stress to its initial shape, then it will give some force which is used in different purpose. For unconstrained type, it will easily recover the shape, and force produced will be zero or constant. But unconstrained type, it will force will be gradually increased, because it will transform from this deformed shape to cubical shape. Right. So This is a smart kit, that is set memory alloy rock splitter kit, which is used in a rover application. Right. Uh, how it will used? First, the rover. There is a robotic application which is drill the rock in different planet, and that will rover will put the set memory assisted device here, and initially it will in switched manner, and by the application of it by some connection with different setup, it will expand and it will indent here and produce the crack, and in this moment it will measure the hardness of that rock. Right. The additional setup will be like this, to measurement of rock hardness in different planet by smart project. Right. This is a tube which is inserted inside the hole, and these are the safe memory alloy. It may be single or multiple type of, and heat operated mechanism which is associated with this small control box. Right. And inside this tube, when safe memory alloy capsule will inserted it, and it is winded by this temperature induced that coil. The setup is like this. The rock sample or rock is there, then rover will drill hole here, and after that it will put this memory assisted device, and again by heating by some means electric operating device, it will indent and crack the surface, and by this time it will calculate the hardness. Because the setup is like this. This main part is memory alloy, and it is winded by different wire, which is controlled by the device, which is here. Okay. The next one is rover wheel. You know, in conventional case, when we'll send material to space, we have to choose very light material and very thin material. So this wheel, it's very little thickness, and when it will move in a different area of a different planet, then due to erosion, this type of defect you can see, and some stone it will struck with it, and easy movement will be not occur. So there is a very difficult to operate them. So this is the rover movement. This small thickness vehicle is there. So due to this problem, it is unable to take photograph or testing very smoothly. So NASA already planned and already developed this type of safe memory alloy wheel, which can operate at any type of surface for easy movement of this robot. So what will how it will work? You just see this video. This is the wheel, and when it will operate at different surface, okay, it is a pseudoelasticity behavior of wheel, and at sunlight at that temperature, it will not uniform. Okay, and it can go at any type of difficulty surfaces. This is the beauty of secondary alloy. And another application is this satellite hinge. The large setup, which is just that is hold some setup is very that is hinged with this satellite, and during escape, what will happen when it will ignite at when temperature will increase, then the setup it will open up, and easy release of satellite will be there. Let's see here. There is a memory alloy hinge, and when temperature will rise, then it will detach, then easy escape will be there. Then satellite damper. satellite damper. In satellite damper here, you can observe very small coil is there that is made up of set memory alloy, and which is operated in such a way that it will consume the bombardment of any other particles, high speed particles or large particles to satellite. Then it will maintain the structure or stabilize the structure, this damper. So it will work like this. Force will exert, then very slowly it will recover. Okay, it will not suddenly. It will not give reaction, because every reaction has opposite reaction. But when it will suddenly react, then structure will be unstable. In this case, this damper will minimize or it will maintain the stability. And this set memory is aeroplane flank or flap here used here in it is a research type of project. So in this, this is used to actuate this part, okay, this flap part, to operate in different or maneuvering in different angle, or it will increase the load or decrease the load. This is the set memory alloy. That is where is attached to this to actuate this part. This part. Okay. So it can maintain the speed. Also, it will rotate at a different angle also. And nowadays, people are thinking about how to maintain the wing, total wing, by set memory alloy beam. Right? We can operate this shape to this shape, and by this shape, by shape changing, we can operate the speed or angle of the aeroplane. And most of the successful application also there, that is laminated or multi-layered set memory alloy wings. Right. And also by observing bird activity, the total shape of the aero vehicle, that is scientists are also thinking about how we can actuate the total shape of the aero vehicle. Right. This is the set memory alloy wired or netted shape. So it can be, the shape will totally actuated by set memory alloy. So this project is going on in different in MIT, and to actuate the total body of aero vehicle, just like a bird. And another commercial application is coupler. Okay, coupling agent, set memory alloy coupling agent. In air aeroplane, suppose aeroplane that want fuel, how to refuel it. So there is a coupling agent is required from source tanker to the required space vehicle, right? Nearly in this the previous year, Rafael, you know about all the data about that, because 4 hour working after 4 hour, so how refueling in air is possible. This type of coupling agent, it is possible very smoothly. Memory alloy is in between this, and by temperature, higher temperature and low temperature, to a set memory alloy is here. We can use to connect the tanker to receiver nozzle and easily actuate in such a way that it will use a coupling agent to refuel it. Another one is satellite antenna. In military application on space vehicle also, that contain very small amount of antenna, you can squeeze and you can hold it in your hand also. Right? Very small volume. But when it will expose to sunlight, when it is required in case of space application or space station, then it will open up to a larger one, and easy communication will be there, right? And also in some military application, they are using also in trench area. If then locomotive, the inkwell type of application, set memory alloy also used. Here you can see this is a set memory alloy part, and temperature is induced at high temperature. It will expand, and the structure is like this. If it will expand, then it will the weight is like this. It will go forward. Okay, it will stable here, and it will come back. So in this way, the locomotion will be there. Okay. The structural arrangement will that, and actuation of stimuli will apply. It's the best application to move the robot also. Then satellites shutter closure. In some satellite that is operated by temperature only, when it will open up, then how to close? There is a set memory alloy. Where is there? Okay. It is a laboratory scale. When it will hit it, and it will close. Okay. Then biomedical stent. In this current age, so many are suffering with cholesterol problem, also blood pressure. What is the reason? The reason is cholesterol and blockage of blood passage. Right. Just look at this picture. Due to this cholesterol deposition in blood vessel, so the movement of blood is very high, and high blood pressure will be there. So there is a different problem. So how we will avoid it? And there is a technique that is stent we can use there to regulate the movement of blood there. So this is the safe memory alloy strength. So initially we will deform it, or we will squeeze it just like this. Section. And here, when you will put inside the blood vessel where passage is very low and creating a high blood pressure, uh, and when you will insert, by getting body temperature, it will open up. Okay, it will open up and squeeze this part, and open the diameter will be open for good blood passage. So it is easily we can maintain the blood flow. Okay, this is the beauty of this biomedical stent. This is mainly in market. It is available nickel, titanium rich nickel titanium safe memory alloy. In dental wire, bone fixation, eyeglass frame, blood clot filter, all of these also made up of safe memory alloy. Here there is a dental wire. Initially, the doctor is stressed in such a way that it will fix to the two side of the teeth. Then, by gaining body temperature, gradually it tend to straighten itself as usual original self. So gradually, by gaining body temperature, it will straighten. At a particular time interval, we have to remove it out to align the teeth. To fix the bone, unaligned bone is there. If we will use if it is not possible to fix it in a conventional type, then we'll fix a safe memory alloy type of material. Then the structure will be like this. It will recover the shape accordingly. So with respect to that shape recovery, we have to maintain the shape of that bone or join the bone. Then blood clot filter. Uh, Also, we can use safe memory alloy to hold the different foreign substance or unwanted substance in the gases, right, or blood clots. We can hold again. We'll from it out. We'll put it out by giving temperature. Will open. Now, in last slide, we will discuss about benefit of safe memory alloy. Okay. First one is noiseless. It is the operation is noiseless. Okay. Smooth and friction-free operation. Then it is a powerful operation, that is a high power to weight ratio. Safe memory alloy can give. Increase with mass reduction, because high power to weight ratio, when you will compare to bulk one and when you will compare with thin film, obviously thin film it will give high power to weight ratio due to high energy absorption, quick energy absorption, and also heat dissipation. For that reason, thin film will be better producing power to weight ratio. Then controllable, that causes no demolition or vibration damage to the surrounding environment or other nearby projects. Okay. It is a very due to this smooth operation. And convenient, it is a convenient operation, this type of applications by secondary alloy. It needs little setup and activation compared to other static models, chemical agent, which can be take a day to react. Right. So in this actuation, only temperature is a very simple setup, temperature-induced memory alloy. Then simple and safe. It is require only heat input to activate. No complex valve system or hydraulic fluid are needed, okay, as comparison to other conventional material. Then it is a compact that has a small volume and extremely low weight, so it can be transported more easily than heavy hydraulic type of weight. Okay. Excellent corrosion resistance, excellent biocompatibility, also have excellent damping resistance, and simple and compact actuator mechanism with comparison to other smart materials. Okay. These are the benefit for which we are going for this safe memory alloy smart material. And what are the limitation? Basically, we will keep in focus for this limitation for all the application, which is if it will alter, then it will give a very huge problem. It will not give the particular runtime activities. Okay, what is these limitations? First one is setup of fabrication parameter. What type of composition you will take, which type of martensite temperature, austenitic temperature, finish, starting temperature you have to fix. Okay, according to that composition, right? And limited bandwidth with respect to the training. And training is also an important factor after fabrication. In fabrication, you will take the composition, then different austenitic and martensite finish and static temperature, and in between temperature you have to operate. You have to first detect with respect to that composition. Okay, that's what we call it is a limited bandwidth with respect to the training procedure. Okay, thank you all of you. So if you have any doubt, you can ask me here. Hello.
Hello. Yes, sir.
If any question you will get, then you can pass to me.
All right, sir. So, do you have any suggestion or feedback to our organization?
Yeah, actually, it is a nice initiative. I have gone through your group. Also, it is a very nice organization and good initiative. And, it's a good platform for interdisciplinary area. it will in near future it will give a very good idea and collaboration with many of these experts also.
Thank you, Professor, for sharing your valuable time and for joining this webinar. I would like to thank all our sponsors and coordinators. I would also like to thank our president. We will happy to hear your comments and compliments or suggestion at our Facebook and Twitter page. This video will be available shortly in our YouTube channel. Kindly subscribe our official YouTube channel, IRAJ Conferences and Seminars, for all past and upcoming webinars and expert lectures. Thank you all. See you another webinar soon.